In this video, we continue our work in section 3.1 using the definite integral. And we're now going to summarize two main definitions that we will see again in this course. So first, Riemann sums. So Riemann is a famous mathematician that came up with a way of estimating the area under a curve by using rectangles. So that work that we already did in examples 1 and 2 are examples of computing Riemann sums. So let's summarize that work here. So a Riemann sum is the sum of the areas of a certain number of rectangles that approximate the area under a curve. So we could say, let's take it off a shape again. So you'd say the sum of the areas under n rectangles that approximates the area under a curve. And we always want to give the area that we're looking at bounds. So we'll say a curve on A to B. So some more notation here. So if we look at the curve of the function f of x, then we denote change of x or delta x as the width of those rectangles. We compute change of x by computing b minus a, so the length of the interval, over n, the number of rectangles we want. So then the Riemann sum looks like the following. Rather, before drawing that out, I'm just going to draw a picture of what we should have in our heads here. So we're looking at a graph of f. We're looking at our interval from A to B. And we want to chunk up our interval into rectangles and compute the area by computing the area of those rectangles. So again, in the previous videos, we looked at a specific method for creating those rectangles, but in general, a Riemann sum doesn't specify the method. So what we were looking at before were Riemann sums with left endpoint rectangles or with right endpoint rectangles. But in general, a Riemann sum is just a way of computing or estimating area by chunking up what we want into rectangles. So then to finish here, we'd say the Riemann sum for the area under f of x on A to B is the following. So let's call the values on our x, on our horizontal axis, our x-axis, x sub 1, x sub 2, x sub 3, x sub 4. So we look at then, so then repeat sum, we would look at the sum to be the addition of all of the areas of those rectangles. So it would look like change of x times f of x sub 1 plus change of x times f of x sub 2 plus all the way up until change of x times f of x sub n. Now, there's a bit of notation that we often use to represent a sum where the terms are very predictable. So we see that we can predict the terms in this sum. Why? Well, what do they look like? They look like a change of x times f of x sub something. So I'll just put in a little I here. And now if we want to talk about all of those terms, what we can do is write this big sigma So this is a Greek letter sigma, capital, and it's often used to denote such a sum. And we also decorate this sigma with our indices. So I, which is here, would start at 1 in our case and go all the way up to n. So if we wanted to write this sum out in a more succinct way, we could write it as the sum from little I going from 1 to n of change of x times f of x sub I. So this is often called summation notation. And again, it's just helpful when you have a large sum like this to write that sum more succinctly like this. So again, these Riemann sums are ways to approximate area under a curve by using chunks. These chunks are rectangles. But we will be learning about another way to actually find the exact area under curves. And that exact area is often called the definite integral. So the definite integral looks like the following notation. We have this soft, long, lazy s of f of x. We say dx from a to b. So just a bit of wording here on the notation. These a's and b's are called the limits of integration. This f of x here is the function we are integrating over. Which means the function we're finding the area under. And then this d of x tells us the variable that we are integrating with respect to. So before I write anything down, just referring back to that Riemann sum. So because we're looking at changes in x as our width, this, if we wanted to describe the area under this curve, we would use dx. So it tells us about which variable we are finding width of, or rather that we are chopping up our area under. So in words, I'll say the variable integrating over. So what is this amount? Well, or this whole object that I just wrote down? Well, this is a number when we have these limits of integration, and it's equal to the exact area under the curve of f of x from a to b. And so again, that's the picture we should have in our head, is a picture of our function f. So it looks like this, our a and our b. And because we have a dx here, we're looking at these slices coming as vertical lines on the perpendicular to the x-axis. So we're cutting the x-axis apart to get our chunk here. And then the exact area is a number that is equal to this entire term. All right, so we will be learning more techniques about how to find those numbers or those definite integrals exactly.